A concrete road looks silent, but inside it, an entire structural argument is happening 24/7. Concrete roads form the backbone of modern heavy-duty transportation infrastructure. From national highways to industrial freight corridors, rigid concrete pavements are engineered to carry enormous axle loads while delivering long-term structural durability. But to understand why they perform so reliably, we must first understand how they behave structurally. A concrete road is classified as a rigid pavement because the cement concrete slab itself carries and distributes wheel loads. Unlike flexible pavements, where stresses move progressively through layered granular materials, rigid pavements behave as an elastic plate resting on a supporting foundation. This fundamental difference in behavior completely changes how loads are transferred to the ground. In flexible pavements, wheel loads transfer through grain-to-grain contact, concentrating stresses near the surface. In contrast, rigid pavements spread stresses over a much wider area through slab action, significantly reducing subgrade deformation. However, structural behavior alone does not determine performance. Traffic loading patterns play an equally critical role. Modern concrete pavement design is based on axle load spectrum analysis rather than simplified easel values. Heavy highways experience single, tandem, and tridem axle loads, often exceeding legal limits, making accurate traffic modeling essential for long-term durability. Yet even the most advanced traffic modeling cannot compensate for poor ground support. The performance of a concrete road depends heavily on the quality of its foundation system. Instead of using CBR, rigid pavement design relies on the modulus of subgrade reaction, the K value, to represent support conditions. For heavy traffic corridors, dry lean concrete sub-base layers are widely adopted to provide uniform support and prevent pumping. To appreciate its importance, we must understand what the K value truly represents. The K value quantifies the resistance offered by the subgrade against slab deflection. A higher K value reduces slab stress, improves fatigue life, and enhances pavement performance under repeated heavy loading cycles. With foundation behavior defined, attention shifts upward to the concrete itself. Concrete mix design for heavy traffic roads is performance-based. High-strength concrete, typically M40 to M50 grade, with a carefully controlled water-cement ratio ensures adequate flexural strength and durability. Supplementary cementitious materials further enhance long-term resistance to environmental and load-induced deterioration. But strength alone does not guarantee durability. Geometry becomes the next decisive factor. Slab thickness is the most critical design parameter in rigid pavement systems. Thickness is determined by evaluating cumulative fatigue damage from traffic loading, as well as edge stresses, corner stresses, and environmental influences over the intended design life. Even then, the slab is never stress-free because temperature itself introduces internal forces. Temperature gradients within the slab generate warping and curling stresses. These environmental stresses combine with traffic loading and must be carefully accounted for to prevent premature cracking. To manage these inevitable movements, engineers introduce controlled discontinuities. Joints are intentionally constructed to control cracking and accommodate thermal expansion and contraction. Proper joint spacing, alignment, and detailing are essential to maintain smooth load transfer and riding comfort. But joints alone cannot ensure structural continuity. Load transfer mechanisms are required. Dowel bars play a critical role in transferring wheel loads across transverse joints. Correct dowel alignment prevents faulting, joint spalling, and differential settlement under repeated heavy axle loading. With structural design defined, precision construction becomes the determining factor. Modern concrete roads are constructed using slip-form paving technology. This method ensures accurate thickness control, high productivity, and consistent surface quality over long pavement stretches. Surface performance then depends on finishing and early age protection. Surface texturing enhances skid resistance, improving safety under wet conditions. Simultaneously, curing compounds preserve moisture for proper cement hydration, because effective curing is essential for achieving full design strength and long-term durability. In recent years, technology has elevated construction accuracy to an entirely new level. Advanced systems such as GPs, machine control, intelligent compaction, and maturity sensors have transformed rigid pavement construction. These innovations improve geometric precision, reduce construction variability, and significantly enhance life cycle performance. Throughout this entire process, verification remains continuous. Quality control measures, including flexural strength testing, slab thickness verification, joint alignment inspection, and surface smoothness measurements, ensure strict compliance with design requirements. And when engineering precision is maintained from design through execution, the results speak for themselves. When properly designed and constructed, concrete roads deliver superior durability, minimal maintenance demand, and exceptional service life under the most demanding heavy traffic conditions. Rigid pavements do not rely on flexibility to survive. They rely on structural intelligence, material science, and disciplined execution. If you found this advanced engineering explanation valuable, like the video, subscribe to the channel, and continue learning with us.